Hey, what's going on, everybody? This is JJ, and in this video we are going to talk about the Apollo 13 mission, and it is going to be an interesting one. And then we also are going to relate stoichiometry and chemical reactions to this very specific mission that helped them stay alive and return back to Earth all in one piece. And so the Apollo 13 mission occurred in 1970, well before I was even born, and so maybe a lot of you that are watching this video have no idea what the Apollo 13 mission even was. And so this will be a fascinating lecture for you then. And so the Apollo 13, we see here a picture of the rocket that lifted off in 1970, and it was consisted of the command service module and a lunar module. The command service module, also called the Odyssey, was tasked with bringing the lunar module, which was inside the command service module, to the surface of the moon. And so then the lunar module could land on the surface where the astronauts could get out and then acquire samples and investigate the terrain and do whatever other research they intended to do while on the moon. Unfortunately, at around the 55-hour mark, right after the astronauts actually was talking with the press and running system tests of the lunar module, which all went well, several minutes after that, they heard a loud bang. And they didn't know at first what the loud bang was. They thought maybe a meteoroid actually hit the ship, hit the CSM. But they didn't have any evidence to suggest that, so they continued to investigate and found that one of the oxygen tanks, oxygen tank 2, was empty when it should not have, and oxygen tank 1 was actually losing pressure. And this loss of pressure indicated that something had exploded. In fact, right before the explosion, around about 95 seconds before the explosion, one of the astronauts, Mr. Liebergott, noticed that there was a malfunctioning readings with the pressure in the tanks, and so he instructed one of the other astronauts to start the fans in the oxygen tanks, and this would allow the contents of the tanks to destratify, and so in order for the astronauts to get a more accurate reading. Unfortunately, it was later discovered that a short circuit occurred and a voltage was generated. That voltage allowed for a combustion reaction to take place, and it exploded. And we can see here that this is what the CSM looks like before and after the explosion. You can see quite a bit of damage. Unfortunately, when they lost those oxygen tanks, there was no fuel to power the CSM, and so it immediately became clear that the new mission was just to return home safely to Earth, not go to the moon. And so they took a step back and strategized and did some computations and decided the best trajectory in order to get back home to Earth alive would be to wrap around the moon and then return back to Earth without stopping at the moon. And so one of the issues they will face during this long trek back home is that carbon dioxide will build up. And this carbon dioxide, if it builds up too much, can remove the oxygen in the air, and the astronauts won't be able to breathe and they'll asphyxiate. So in order to prevent this, the astronauts need to create lithium hydroxide canisters, masses that react with carbon dioxide, in order to remove that CO2 from the air that they're trying to breathe in within the modules. Unfortunately, they had a couple canisters, but that wasn't enough for for all of the astronauts during the return home from the lunar module. So they had to do some makeshifting and creating their own little lithium hydroxide canisters with the materials they had at their disposal. And so let's do a little bit of stoichiometry to make this ever more interesting. So we could write a chemical reaction. That chemical reaction we know now is lithium hydroxide. So lithium OH, which is a solid massive object, reacts with plus CO2. And this produces lithium OH3, I believe, plus some water. and the water is a liquid. And so this is also a solid, and this is a gas. We could throw gas in here. I can't fit solid in here, so just know this is a solid as well. And so let's make the assumption that the amount of CO2 that will be exhaled during cellular respiration by each astronaut is 1 kilogram per day. And the astronauts calculated that the amount of time they would spend in flight, we'll say, is roughly 6 days. 6 days. And there are 3 astronauts that are breathing, so that are producing CO2. So given this information, how much CO2 is going to be entering their little cabin? Well, we have 6 times 1, so 1 kilogram per day, so 6 days, so 6 kilograms total for 3 astronauts. So we do 6 times 3 equals roughly a total of 18 kilograms. And if we do some conversions, we know that kilograms means kilo means 1,000. So we really have 8. Move the decimal place 3 places. 1, 2, 3. We have 18,000 grams of CO2. And so how much lithium hydroxide do we need to react with the CO2? Well, we need at least the amount of carbon dioxide. And in order to understand or to identify how much that is and calculate it, we need a standardized unit that we can apply across all molecules, and that is what we call the mole. So how many moles is 18,000 grams of CO2? Well, first we need to calculate 1 mole of CO2. And so carbon has a molar mass of 12 roughly, very roughly, plus oxygen, which is around 16, and we have 2 atoms of oxygen. So we multiply that by 2, do some basic arithmetic, we get 26, 32, 40, 44 grams per mole of CO2. And so now that we know that, we can take our 18,000 grams and divide it by 44 grams per mole. Grams cancel out. 18,000 divided by 44 is, let's see, it is equal to 409.09 moles. And so I think we actually forgot a step. We forgot a step. What did we forget? We forgot to balance this equation. We can't have it unequal on both sides. So if we throw a 2 here, 2 lithium, 2 oxygen, 2 hydrogen. So 2 lithium, 2 lithium, 2 hydrogen, 2 hydrogen. Oh my god, this is CO2. Whoops. This is not correct. This is actually supposed to be lithium carbonate. There we go. So 2 lithium, 2 lithium. 1C, 1C, 4O, 2O plus 2O is 4O, 2A hydrogen, 2 hydrogen. And so there we go. Now we're balanced. And so the mole ratio for lithium hydroxide and carbon dioxide is 2 to 1. So if we come down here, you can say the mole ratio the mole ratio is equal to 2 to 1. And so we take that 409 moles and we multiply it by 2. And this gives us 818.18 moles of lithium hydroxide is required in order to react fully with carbon dioxide. So now that we know that, we can convert this 818 moles to grams if we wanted to, but we could also say that's the answer. This is the answer. This is the answer. We need 818.18 moles. But if we were to convert it, we would, lithium is about 7 roughly. No, we'll round, we'll say 6.9. 6.9 molar mass plus the oxygen, which is 16 roughly, plus the hydrogen, which is 1, which is roughly 23.9 grams per mole. And this is going to give us 23.9 grams times 818.18 moles. This is grams per moles. These cancel out, and we get roughly 19,554.502 grams. And those grams, if we do it in scientific notation, we get 1.96 times 10 to the 4th, because we move this 1, 2, 3, 4 decimal places. 10 to the 4th grams. And that is also the same as 818 moles. And so that's the answer. And I thought that was a pretty cool video we could do on stoichiometry and make it a little bit more interesting than maybe it seemed. And I'm happy that these astronauts made it back alive. And they had to do chemistry in order to make that happen. And so with that, we'll see you in the next video.